So now we are going to solve questions of a new part in this principles of mechanics, that is gravitation. Okay. So question number 1.210. It is saying a cosmic body A moves to the sun with velocity v naught and aiming parameter is L and the arm of the vector is v naught relative to the center of earth. Okay, our diagram is given for our support, that it is trajectory of this object. Sun is at this point. Okay. This is v naught velocity of this cosmic object, and this aiming distance is L. Let's see, assume sun lies at the center. Okay. So find the minimum distance by which the body will get to the sun. What would be the closest distance? Okay. So whenever this we measure the distance of the body or this cosmic body from the sun, it means we want to measure a perpendicular distance from the velocity vector of this object and this sun. Okay, so let's assume the minimum distance of this cosmic object from sun is r minimum. Okay, this is minimum distance what we want to figure out. So here we can apply two principles. First principle is conservation of angular momentum, and we want to find out that angular momentum about this point C. Okay. So first let's apply concept conservation of angular momentum. Okay. So as we know that angular momentum is moment of linear momentum about point of rotation, or you can say point of reference. So if mass of this cosmic object is m, so its initial momentum is mv naught and this approach distance is L, so its initial momentum will be mv naught into L, angular momentum. Okay. And at this point when distance is r minimum and velocity is v, then angular momentum will be mvr minimum. Okay. So we can find out velocity at this general point in terms of r minimum. M and m will be cancelled out. So this is v naught L upon r minimum. This is our first equation. Okay. Now we can apply second alternative concept, that conservation of total mechanical energy for this system. Okay. So let's assume mass of sun is ms. Okay. Here. Now at this point there is kinetic energy only, that is half mv naught square. So we are applying conservation of energy. Okay. So at this point energy is half mv naught square, and when object reaches at this point, then there will be two components. One is kinetic energy, another is potential energy. So potential energy for any gravitational object is g, mass of the object, mass of the sun divided by distance between these two, r minimum. Okay. And kinetic energy is half mv square. Now we can substitute value of v from equation number 1 in this equation. So we'll get 1 over 2 mv naught square minus gm into mass of sun upon r minimum plus 1 over 2 mass of the object into v naught square L square upon r minimum square. Okay. So we can further simplify this equation and frame a quadratic equation. So m will get cancelled out from this entire expression because it is common everywhere. Okay. And we can multiply by 2 and r minimum square in this equation. So we'll get r minimum square into V naught square from this term is equals to minus G mass of sun into R minimum, okay, and twice of it, plus V square L square, and that's sufficient. This is our equation. So we can frame a simple quadratic equation. So we can write R minimum square plus 2G ms into G into R minimum upon V naught square plus L square is equals to 0. Okay. So here we can apply a basic approach for finding the root of equation. Okay, that is R minimum is equals to minus B, this part, to ms into G plus minus under root B square minus 4AC, so square of this term, ms G to whole square minus 4 times this term, 4L square upon 2A. Okay, so this is minimum distance in terms of all these parameters. So this is the minimum distance of the object. We can further simplify this expression by taking out this term ms over G common from this expression, but no need to do that exercise if it is not required. Okay, and please note here this capital G is universal gravity constant.